Can you see my screen now?
Yes, sir.
All right. So before I start today's lecture, uh, let me announce that we will have a minor exam on 23rd. So ours is A slot. So A slot is 23rd in the afternoon after lunch. So I'll send an email regarding that, mentioning the details. So it would be on the same lines as we had the quiz. So it would be via grade scope. You have to follow the same instructions. So and the other thing is that I will give this time because most of you were complaining about timing, so I'll give a few minutes extra. So like it would be around 1 hour for 1 hour 45 minutes or 1 hour 40 minutes. So for 5 6 questions. We'll see. The second thing is that as you demanded, I have already uploaded the practice problem sheet on Moodle. I have also shared this with you via email. So I hope that you have tried that. Even if you haven't, you can do it like before exam. What I want to say is that I would like to have a discussion session just to see how you guys are thinking and how you guys are writing on those problems. Those are like you have to write and you have to show something. So I gave specifically those problems based on the kind of problem you were having in thinking and in writing. So just let me know if you want to have a discussion session. If not, that is also fine. That is all up to you. But if you want, we can have a like 1 hour, half an hour, or 1 hour, depending on your how much you are free. We can have a discussion session in the afternoon today, or maybe tomorrow. So whatever. So tomorrow would be a bit tight for you because then after a day the exam starts. So you must be busy in you might be busy in some other things. So we can have a discussion session or a problem session today in sometime in the afternoon. So if you are free then. So what do you think? You want me to have a problem session? I will discuss only the problems uh, which I have given in the problem sheet. I mean the practice problem sheet.
Yes, sir.
Yes,
Yes,
sir.
sir.
So it's not mandatory for all of you to join. Those who want to who want to have discussion on those problems, then we can have. Otherwise, like it's not like you are like forced to join that session. Even if 2 3 guys are there out of 70, it's okay. We can still have that. So what time you suggest today?
Sir, it will be in evening, please, because between 2 to 3 we have a
Hmm. So
Sir,
sorry,
up to 3 we
between
have
2 to 3 we
classes.
have tutorial.
okay, after 3 you are saying?
Yes, sir.
Sir, can we have
Okay.
after 4? Yeah, maybe on 4.
So ठीक है. So we can have it, let's say, from 4 to 5. Is it okay?
Yes, sir.
Okay.
Yes, sir.
So okay, fine. Then we will have a problem session, or this just like a informal discussion on the problems you are having, and we will discuss how to prove the results which I have given in the problem session, in the problem sheet, practice problem sheet. All right, so let us start today's lecture. Today is lecture 12. So if I recall from a previous lecture, from the last lecture, what we did, so we saw that if we are given a vector space, then we can talk about its dual space, which is just the collection of all linear functionals. That means the linear transformation from vector space to the field. And in particular, then I mentioned that most of our theory in this course would basically depends on, or which will be considered only for finite dimensional, and whenever needed, I will mention the results for infinite dimension also. Okay. So now if suppose you have a finite dimension vector space and suppose that you have a basis beta, let's say v1 to vn of basis b for vector space v containing the vectors v1 to vn, then we can find a basis of depending on this base given basis we can find a basis for the dual space, uh, which is like f1 to fn, and this basis satisfy this property that fi vj is equal to del ij. That means it is equal to 1 if I equal to j, and it is 0 if I is not equal to j. Then this basis is called dual, is the dual basis of given basis. Okay. Now then we saw some example. Then I gave you one at the end of the lecture. I gave you one more example, and then we saw that uh, if we have a so if we like proceed in the other direction, like we start with a basis of the dual space, then for that example, that particular example, we were able to find a basis for the vector space of which the given basis of the dual space is the dual, right? Then at the end of the lecture, I had put up this question that can we do it in general? So let me start by putting up this question again, and then we'll try to answer this. Okay. So the question that we have in hand is the following: for a given basis, say b dash of containing the functional f1 to f1 of the dual space v dash, the question is, can we always find a basis of v of which v dash is the, this is the question. Okay. So we'll try to answer this question in today's lecture. We'll answer this by considering the dual of dual space. So that means dual of v dash. V dash is also a vector space. So whatever we were talking about v, we can also talk about v dash. So let us consider the dual of v dash. That means the dual of the dual space. This is called as the double dual of v. Okay. So let me just point this out. So we'll answer this by considering v dash dash, which is, you can also write as v double dash. This is called the dual of v dash, or you can say double dual of v, right? Okay, so we want to answer this question. So before we proceed further, let us make this observation. So let us make this observation here. Let let us suppose that we have a, so basically what we are trying to do, see, we are given functional a basis of the dual space, and we want to find a basis of we want to find a basis of v. We want to find a basis of v such that b dash is the dual of v. So basically what we are trying to do, from f1 to fn, we want to find vectors v1 to vn that satisfy fi vj equal to del ij. This is what we are trying to do. Now what I'm saying, so let me give you this idea. So what we have v dash right now, and we want to find basis for v such that the given basis of the dual space is the dual of this basis. Right? Now what I'm saying, instead of, so to find vectors here, so given this f1 to fn here, I want to find vectors here, right? So what I will do, instead of so these vectors I will find by somehow going to the double dual of v. So I will, so what I know so far is that if I'm given this, if I'm given this f1 to fn, then I can always find dual basis of this, because as whatever we did for a vector space, we can apply the same thing on this basis, and we can find some basis, let's say L1 to Ln of this V double dash, which is the dual of this f1 to fn. So that means this Lifj satisfy this del ij. This we can do. This we have studied. Now what I am saying, we want vectors here, right? So what I will do, I will somehow try to connect these functions Li on the dual space such a way that I am able to generate a basis of this vector space V such that Fivj is equal to del ij. So this is what I want to do. Now how I can do that? So one way is that if I somehow relate these two, if I somehow relate these two, V and V double dash. If I somehow relate these two here, then I can do somehow say that okay, if I L1 to Ln are elements here, and if I somehow have a isomorphism kind of thing, then I can generate vectors V1 to Vn here. Then at least I will have some vectors here, some choice of vectors V1 to Vn here, and then I will see whether these vectors which I have generated using some isomorphism between V and V double dash, can I like can these vectors V1 to Vn solve our purpose? That means can we'll see if Fivj satisfy this del ij thing or not. So this is what I'm trying to do now. So I'll try to first establish an isomorphism between V and V double dash. Then if I have an isomorphism, then you know that isomorphism is 1 1 and on 2. So corresponding to each of these L1 to Ln here, I will be having some vectors V1 to Vn here. And then I will try to see whether these vectors satisfy this thing or not. Fi Vj is equal to del. So this is what is the idea. This is what I'm trying to do next. Okay. So let us make this observation first. Suppose that we have a vector V in the vector space V. And okay, so we have a vector in the vector space V, and consider this linear functional on V dash, because we want to relate the vectors in V and V double dash, right? So V double dash is what? V double dash is the dual of V dash. That means it is a collection of all linear functionals on V dash. So consider this, which is defined by how we define this. I will send. So I'm defining this map here depending on this vector V. So you can see L subscript V. So how I'm defining this? I'll take any linear functional, any element in V dash, and I will send it to f of V. Then you can verify that this is a well-defined rule, this is a well-defined function, and not only that, it is an element of V double dash. That means this is a linear functional on V dash. This you can easily verify, right? Just take f1. So why this is linear? Because you can check that you take any alpha f1 plus f2 here, then by definition it will be alpha f1 plus f2 of V, but then you use this property of functions, and then you can say that it is just alpha lv f1 plus lv f2. So this is linear. So for every vector V, you can find, there is a way to find uh, or to obtain a linear functional on V dash, or to obtain an element in uh, V double dash, right? So now this way we'll see, if I send every vector V to this LV, then I can relate these two spaces V and V double dash. I will see whether this mapping is an isomorphism or not. So what I'm saying is the following, and this is in fact an isomorphism. Let us prove this. So if I have a, let's say, vector space V, I'm talking about finite dimension, so let me mention this. So suppose that we have a finite dimension vector space, then then the mapping T from V to V double dash, how it is defined? Defined by, you take any vector V here and send it to L of V, L subscript V, where L subscript V is defined in this observation here. Okay. So now you know that for every vector V, this LV is an element of V double dash. So you can do this. This is a well-defined thing. Or you can check this. So this is a well-defined thing. Not only that, you can see that you can show that it is an isomorphism. So then the mapping this is an isomorphism. All right. So let us prove that. Why this? This is very easy to prove. So for isomorphism, you first check that this is whatever I have defined here. This is a well-defined thing. The first thing is that whether it is a function or not. First you check the well-definedness. Then for isomorphism, you check linearity, one-oneness, and onto-ness. Right. So let us see first that this t, this whatever function I have defined, it is a well-defined function. T is well-defined. Now, how to check that T is well defined? As by definition, you just take two vectors V and W and say that V is equal to W. And using this, you show that T of V is equal to T of W. That means L subscript V is equal to L subscript W. This is what you want to show. Now you tell me how to do this from this step to the next step. If V is equal to W, then clearly we can say what we want. So see, first you see what we want.
FV
Uh,
goes to W.
yeah. So you can see from here that if V equal to W, then that means f of V is equal to f of W, and this is true for all f in
All V and W.
V dash, right?
Yes, sir.
But then what is this? This is just by definition L subscript V f is equal to L subscript W f. This is true for all f. Now, can you say from here that L V is equal to L W?
Yes, sir.
Yes, because LV is just a function from V dash to here, V dash to F, and it is true the function value of LV and LW are same at every point in V dash. So that means these two functions have to be same. So this is a well-defined thing, right? Next, check that T is an isomorphism. So for this, first check that T is linear. Now for checking T is linear, we just use the definition of linearity. So that means you just take, let's say, alpha u plus v, right? Then by definition, it would be L alpha u plus v. But what does it mean? So this is an element here. So this is an element in v double dash. Okay, so what you can say from here that this is actually equal to alpha u plus v. This is a map from v dash. So this is an element in v double dash. That means it is a linear function on v dash. So it's a function from v dash to f. So that means this is equal to alpha u plus v f. Right? This way you can write. But then what is right hand side? Right hand side is f. By definition, it is f alpha u plus v. Right? So this is for all f we are saying. Now what does it mean? This means alpha f of u plus f of v, because f is a linear functional. So here f is in v dash, right? But then what you can say from here, this thing you can write as alpha L subscript u f plus L subscript v f. But then what it is, again by definition, this is just t of u plus t of v f. Now from these two things you can say clearly that t alpha u plus v is equal to alpha t of u plus t of v, and this is true for all scalars alpha and all vectors in, right? So clearly t is linear. Now check t is 1 1, let's say. Okay. Now if you show that t is 1 1, then clearly it would be an isomorphism. Why it would be an isomorphism? If I just show that t is 1 1, then
Because dimension of
Because dimension of v equal to
dimensions.
dimension v double dash.
so
Dimension
why
equal.
yeah, why dimension of v double dash is equal to, let's say, n, which is the dimension of v. So let's say dimension of v is n. How do you know that dimension of v double dash is also n?
because
Yes.
dimension of v days is also n, and we have defined जो हमने टी टी जो डिफाइन करा वो हर वी के करस्पॉन्डिंग कर रहा है.
Hmm. So dimension, you say dimension of v dash is also n, because v dash is all linear functionals from v to f.
So
So it would be, now dimension of v dash is n, then you use the same logic for v double dash also, that v double dash is the dual of v dash. V dash is of dimension n. So by the same logic, you can say that v double dash is also of dimension n. So now let us check that whether t is 1 1 or not. So for 1 1 is, I will take a vector, let's say in the null space of v, and then I'll show that this v is equal to 0. And we know that this is enough to say that t is 1 1. So let's say that t of v equal to 0. Now this means lv equal to 0, right? Then what? If lv equal to 0, we want to show that v is equal to 0, the vector v equal to 0. Now from here what we can say? From
F v
here,
equal to
F equals to 0.
yeah, lv is a function from v dash to f, and if this function is 0, that means this function value is 0 at every point, but the points are the functionals on v. So it's lv of f equal to 0. But then by definition lv of f is f of v equal to 0, and this is true for all f in v dash. This is true for all f in v dash. Now from here, can we say that v equal to 0? So f of v is equal to 0 for all linear functionals on v. Can we say from here that v is equal to 0? What is your answer?
yes, v equal to 0.
Why? So you are saying that from here we can say that v is equal to 0. Now,
F identity map
why?
होगा उसके लिए भी होगा.
Identity map. Identity map is always between the same space, right? V2, it should always be from the domain to the codomain should also be equal to domain. Then only you can talk about identity map. Here f is a functional, that means it's a map from V to f. So why this is 0? So see here, this equation, this expression here is 0 for all linear functionals on V. But do you have some specific functionals that you can use? So this is true for all f. So if in particular, if you choose some functionals and show that v equal to 0. Can you recall something from last class? So we have a vector space V. So we can take any basis of this, let's say V1 to Vn. And for this basis, we can find its dual basis and F1 to Fn, let's say. And we know that these dual bases are actually the coordinate functions. That means if you look at image of fi of v for any I, then it is actually the ith coordinate of v when it is written in as a in the basis in the given basis v. So what I'm saying is that this is equal to 0. Equal to 0. Why? Because you just choose coordinate functions. Function. So you convince yourself that this is true. So why this is true? You know that you V is a, so let me just do some rough work here. Why to explain this? V is a vector space, right? So you can take any finite dimension. So you can take any basis. Let's say this. Now for this basis, you can always find this F1 to Fn. Let's say of V dash, right? So if it is a dual, then satisfy this. So now you have to show that this V is 0. So this V you can write as alpha I Vi for some alpha I, right? So there would be some alpha 1 to alpha n such that V can be written as a linear combination of these. If you show that each of these alpha i's are 0, then you are done. But now from this expression here, it says that f of v is 0 for all f. Whatever be f, and this fi's are all linear, also element of this v dash. So it will also hold for this. So from here, what you can say that fi of or fj, let's say fj of v is equal to 0 for all j. But fj of v from here, what is this? Is just alpha j. So alpha j is 0 for all j. That means v itself is 0, and therefore v equal to 0. Is it okay? So
Yes, sir.
yeah, you convince yourself. Yeah. So if t is 1 and then we know that t is v and v double dash both are of same dimension, and therefore you can say that. So let me just write this for your records. T is uh, t is also onto, sorry. Why? Because dimension of v is equal to same as dimension of v dash, and it is same as dimension of v double dash. And this implies that T is an isomorphism. So this is nice because now we have a way
सर
to
सर
relate
अगर
vectors. Yeah.
डायमेंशन वाला करना
Yes.
यूज करें फिर चीज और कुछ कैसे प्रूव करेंगे इसमें कि मान लो कोई
Is
पूछे कि डायमेंशन v इक्वल टू डायमेंशन v डबल डैश प्रूव करो देन वी डिफाइन दिस मैप
yes. You can
सर
do
इसको
that
आंटू सर
also.
आंटू इंडिपेंडेंटली कैसे करेंगे
So onto, you know that there are many ways. So if you remember the proof of proving that if you have a linear function from V to W, where V and W have the same dimension, right? If they have the same dimension, then there is a it's enough to show that 1 1 is equal to 1 1 is equivalent to on 2.
सर इसमें रैंगुलरिटी थ्योरम का यूज करके कर सकते हैं ना?
So in fact, we use rank nullity theorem only in that proof. So we are using that result here. So there independently also you can show that. So you can show that these whatever functionals you have defined here, because you know that this what is V double dash? V double dash is a dual of V dash. So for every V dash, if there is a basis of V dash, then you can find its dual. So you know actually the dimension of V double dash. You know the dimension of V. So this is known. You use this fact, and then also you can show that without using this, you can show that if there is an element, let's say L in V double dash, then you can find a vector V in V such that T of V is equal to L. But in order to define this, actually you are using the fact that I mean not explicitly, but inherently you are using the fact that they have the same dimension. Because then only it is true. It is a if and only if condition that if T is a linear map from a vector space V to W, which have the same dimension, then 1 1 is if and only if onto ness. So ultimately you are using the same thing both way. Anyway, so now we have a way to connect elements in V to elements in V double dash. Okay. So what I was saying is here the onto-ness you can use in this way. So um, not onto-ness, but yeah, the fact that this map is an isomorphism, so you can use now, or let me make this observation first. So what we learn, so if suppose
Sir, your voice is breaking.
we have a finite
Sorry,
dimensional vector space, right? Suppose we have a finite dimensional vector space, let's say V,
sorry, your voice
and
is
if I take
breaking.
any element, let
Hello.
any element L. So my voice is not clear.
Yes, sir.
Okay, just a minute. Just a minute. Let me switch the. Just a minute. Yeah, just a minute. Hello.
Yes, sir.
Yes, sir.
Yeah. Can you hear me now? Is it okay? Is it better now?
Yes.
Yes, sir.
Yeah. Okay. Fine. So what I was saying is that let us make this observation. Suppose that we have a vector space V of finite dimension, and that means if I take any, so let us suppose that we have a vector in V double dash. So vectors are of this form here. So let's say any element L in V double dash. Then we know that because of this isomorphism, there exists a vector V in V such that T of V is equal to L. This is because the isomorphism is also onto. So using that fact, T of V is equal to L, right? But what is T of V? T of V by definition it is L subscript V, right? This is how we are defining. L of V is equal to L subscript V. So what I'm saying from here is that So for any L in V double dash, we have a vector V, unique vector. So this vector is unique because it's 1, 1 and on 2. We have a unique, we have a unique vector V in V such that L is equal to L subscript V. So L is equal to L subscript V means what? So this means, so these are actually L and LV, they are element of V double dash. That means they are functionals from V dash to F. And if these two things are same, that means you can say that L of F is equal to L underscore L subscript V F is is true for all F. But then what it is? LV of F is just F of V. So this is true for all F. So for any element, so observation says that if you have any element L in V double dash, then there exists a unique vector V such that L is equal to L uh, subscript V. Okay. Now using this observation or the information from the previous this isomorphism, we will now answer the question. Whatever question we had asked at the beginning, we'll answer to this question. So this answer now, this question now can be given as a corollary of this isomorphism. So let me write this as a separate result here. So let us suppose that we have a vector space of finite dimension over a field, let's say F. Then each basis for, let's say, V dash is the dual basis of some basis for V. Okay, so whatever basis you take uh, for V dash, you can always find a basis of V for which the given basis is the dual. All right. So we have to do it for each basis of V dash. Now you tell me how to start this proof. So we are given a finite dimension vector space. And then using this, we have to prove that each basis of V dash is the dual of some basis for V. So that means if I take any basis, so I have to start with any basis of V dash. So let's say we have a basis of V dash. And then for this basis, I have to show that there exists a basis of for V that satisfy this dual property. So how should I start? What should be my first line?
Any arbitrary basis of V dash.
Yeah. So let us suppose that this B dash containing these functionals f1 to fn, this is a basis of V dash, let's say. Okay. Now this much I know, this much I have a basis. Now using this basis, I have to find a basis for V. Now you tell me, how can I do that? I mean, so we need vectors in V. And then we'll see whether these vectors solve the purpose or not. But how to generate these vectors? What we can say from here?
So sir, can you please once again say what you said?
So the question is that we have a basis for V dash. And we what is our aim here? Our aim is to find a basis for V such that this V dash is the dual of this basis. So this basis of V means we need to generate vectors in V, V1 to Vn, such that Fi Vj is equal to del I. This is what we want. But how can we reach up to that point? From this, what should be my next thing? What I can do?
सर बी डेज की डुअल बेसिस मान लेते हैं L1 L2 Ln.
Okay, so yeah, this is the way as I explained at the beginning. We have a basis for V dash, so we know that there exists. So for every basis, we can find its dual basis. So there exists, let's say L1 to Ln, as you said. This is a basis of V double dash, such that such that, so let's say this is B double dash. So this such that B double dash is the dual of B dash. We can do this always, right? So it's a dual means it satisfies this LIFJ is equal to LIJ for all IJ. This is fine. Up to this is okay. Now what would be the next step? So we have generated elements in V double dash. Now what?
Now we define a map from B dash to basis of V, which is isomorphism.
So we can use this isomorphism. So we have, see, now we have vectors in V double dash. That means these are L1 to Ln. Now using this isomorphism, I know there is a way to generate vectors in V. So I can always find L1 corresponding to this L1 to Ln. I can always find vectors V1 to Vn. What are these? If you look at this observation, for any L in this, I can find this V. For every L, I can find a unique V such that L equal to L subscript V, right? So here L1 to Ln, that means there exist unique vectors V1 to Vn such that Li is equal to L of L subscript Vi, right? So I'll just use this isomorphism. So this implies that there exist vectors, let's say V1 to Vn. Let me call this set B. I don't know whether this is the basis or not, but I know that there exists a set V1 to Vn, or the vectors V1 to Vn, subset of V, such that Li is equal to Lvi for all I equal to 1 to n. Is it okay?
Yes.
Yes, this is because of the observation we just made, because of that isomorphism. Now you look at this thing. What is this Fi of Vj? So say not that. What is this Fi of Vj? Now you see, by definition, this Fi Vj is just L Vj Fi, right? But then Lvi is equal to Li, so I can write this as Lj Fi. But then you look at here, this is equal to del Ij. So this whatever vectors I have obtained here, V1 to Vn, they satisfy this property, the dual property. So now I'm writing that this implies that P is a basis of V such that B dash is the dual, or of which B dash is a dual, and we are done. Now the last statement you justify why this is true. Can we say from here that B is a basis? So clearly, because of this property, if we just show that these vectors V1 to Vn, they form a basis of V, then because of this property, it would be B dash would be the dual of this V. So we just need to say that V1 to Vn form a basis for V. Now, since we know that V is of dimension n, these are n vectors. So if we just show that these n vectors are linearly independent, then that means that this is the basis of V, and because of this property here, because of this property, it satisfies the dual property, and will be done. So the only thing is to show that these vectors are linearly independent. Now can you show that these vectors are linearly independent?
Yes, sir, we can show because dimension of V equals to n.
So
Then we take a linear combination, uh, and
so
then
in order, you have to show that these vectors are V1 to Vn are linearly independent. So if you want to show that these vectors are linearly independent, So what you will do, you will take alpha 1 v1 and so on up to alpha n vn equal to 0. And you have to show these alphas are 0. Now why these are 0?
Yes, sir.
Why these are 0?
सर दोनों और कंपोजिशन
Why?
करा के एफ अल्फा
No, you just look at this thing, na, here.
Sir, by applying FIs.
Yeah. So you just apply fi on this.
यस सर
Then it would be just, so you apply fi, then for each I you will be able to show that alpha is 0 and therefore, okay. So this you can verify.
Yes, sir.
So let me just write this so that you keep in mind why p is linearly independent. Okay, so you think about it. All right, so let's introduce one more term here. This is called annihilator of a subset. Okay, so let us define that first, what it is. Annihilator of a subset. So suppose that we have a subset S of a vector space V. So this is just a subset. Not saying subspace, it's just a subset. Okay. Then for this set S, the annihilator of S is denoted by S naught. This is the notation we will use to denote the annihilator of S, and defined as, how it is defined? It is the S naught, the annihilator of S is the collection of all linear functionals on V, that means all elements of V dash, such that f of V is 0 for all V in S. Okay, so that means you just collect all those functionals on V that annihilates S. Annihilates means if you take any vector V in S, then f of V is 0. Okay, so this is the definition of annihilator. Now you can verify that whether S is a subspace or not. So here I did not assume anything on S. S is just a subset. Whether S is a subset or not, S is a subset of S is a subspace of V or not, S naught, that means the annihilator of S, is always a subspace of V dash. So you can see that this S is a subset of V, but S annihilator is a subset of V dash. Not only a subset, you can show that S annihilator is a subspace of V dash. So this S annihilator is a subspace of V dash regardless of S being a subspace or not. Okay, so this you can easily verify. So I leave this as an so S node is a subspace. Now by definition, you can also say what would be the annihilator of zero space in V. So S is any subset. So I'm saying that subset containing the zero vector only. So what would be the annihilator of this?
V days.
It's V
V dash.
dash. Yeah. And what would be the annihilator of V?
0.
0.
0, sir. Yes, sir.
Okay, all right. This you can verify easily. Why this is? Just use the definition. Now, this using this annihilator, you can prove a very interesting result. It says that the dimension of W. So W is a subspace, or W is a subset of V, and S annihilator is a subset of V double dash, V dash. Sorry. But then you can say the following. let me write this as a result. So if we have a let's say subspace of a vector space V. So let's say now this W is a subspace. Then dimension of V, and assume that V is finite dimension. Okay, so this is finite dimension vector space. Then the dimension of V is equal to sum of dimension of W plus sum of plus dimension of any letter of W. So let us prove this. So how to prove this? Suppose that the dimension of okay, you tell me how to start. So what we have to do here? We have to show
डब्ल्यू
the
की
dimension of
डबल
yeah, W की basis ले लो, right? So you are saying that take a basis of W. So let's say D be the dimension of W, and because of finite dimension, so W would also be finite dimension, and let W1 to WD, this is the basis of W. Okay, then
सर इसको extend
Extend basis.
extend कर दिया. So
एक्सटेंड
let's
कर
say
देंगे सर.
okay, let me extend. So you are saying that you just add few more vectors. So let's say I'm adding these WD plus 1 to WN, so that it becomes a basis of V. Now what?
सर अब इसकी dual basis मान लेते हैं f1 f2 dot dot
Okay,
fn.
so let's take F1 to FD, FD plus 1 to Fn. This is the dual basis of B. Then what? So you have started in the right direction. So you were given a subspace W. So what you did, you took a basis of this. You have a basis of this, so you can always extend this basis to a basis of V, which you did. Now what you can do, you can take a,
Now,
you know that there is a dual basis, so that is also fine. Now you have to show that dimension of W is equal plus dimension of W nor is equal to N, right? So what you have to show, basically you have assumed that dimension of V is N here. You have assumed that dimension of W is also D. So what you have to show from here, that dimension of W nor is equal to N minus D. Then you are done. If you show the dimension of W nor is a subspace of V dash, right? So in order to say that dimension of W nor is equal to N minus D, what we can do here? So what should I look for?
The claim that FD plus 1 dot dot Fn is a basis of W naught.
Right. So that is the right thing, because what we need to show now, our claim is to show from here that dimension of W nor is equal to N minus D. So in order to say that dimension of W nor is N minus D, that means I need to find a basis for W nor containing N minus D elements. Now here I already have some linearly independent vectors in V dash, right? So out of these, if I choose, if I use these bases and show that some of these vectors, or let's say N minus D of these vectors form a basis for W naught, then I'm done. And the choice for this is clearly FD plus 1 to Fn. Right? So can you tell me? So you said that you show that these form a basis, these functional form a basis for W naught. Why have you not started from here? You have not considered any of these.
Because sir, F1 of V equal to 0 and FD of V equal to 0 in W naught.
Yes,
Yes, वो
because
LD हो जाएगा.
they form a basis for W. So clearly, because of the duality, the values of these vectors are 0 for these functionals at least, and for these vectors, for these functionals, there would be at least one vector here for which the value is equal to 1, so it is non-zero. So clearly they are not the candidates. The candidates are these one, and we'll verify. Okay. So this is what we have in hand. So we'll prove that. So we'll show that in order to prove this thing, we'll show that W nor is actually span of fd plus 1 to fn. Why it is enough to show? Because we know that these are already linearly independent because they are coming from this basis b dash. So we just have to show that these functional span W nor, and then we are done. Okay. Now one thing is clear. So these are two sets. We have to show that these two things are same here and here. So we'll show that one is contained in other, and same way the other side also. Okay. So let us. So I'm saying that clearly one side inclusion is straightforward. That W node is contained, not W node, but the other this direction. That uh, this is straightforward, or not straightforward. Then you can easily check that. Why this is true? That span of this is equal to this is contained in W node. So why this is true? Let me show that fd plus 1, because of the duality here, this b dash is the dual of v, fd plus 1 of w. So for any w in the subspace w, what is the value of this? Let's say d plus j for any j
0.
is 0. Why?
0.
Why?
Sir,
बिकॉज W is a linear combination of W1 to WD, और फिर
Right,
इसको अप्लाई करेंगे तो वो जीरो हो जाएगा.
right. Absolutely. So because
sir, by
w is
definition.
an, yeah, by definition w is an element of w, and we know a basis for this, which is this one. And then we know that these functional, they satisfy these duality property. That means this fiwj is equal to del ij. Using this, the value of these on these is 0. So this is 0 for all j from 1 to n minus d. But if this is true, then can I say that this implies what? What does it mean? If for any w this is satisfied, then what we can say from here? Can we say that this f d plus j belong to w annihilator?
Yes.
Yes. If each of these vectors, these functions f d plus j from j equal to 1 to n minus d, they belong to the w annihilator, can we say that their span is also belong to w annihilator?
Yes, sir.
Yes.
Why?
Subspace.
Yeah, it's a subspace. W naught is a subspace. These are elements, so their span would also be there. So this implies that span of fd plus 1 to fn is subset of W naught. Fine. Now how about the other direction? So we have to show that the other direction is true. That means if you take any now element in W naught, so element in W naught is would be of the form f. It would be a functional on V. So let's say f is in f is an element in W naught, any element in W naught, right? What does it mean? If f is in W naught, then clearly f of W is 0. So now let f is in W naught, then this implies that f of W is 0 for all W in W, right? By definition of this annihilator, so f belongs to annihilator, so that means this is true. Now we have to show that this f is actually linear combination of This one, it's in the span of this. Now can you tell me how to do that? Can you tell me how to do that? See, this f is in W annihilator, right? F is in W annihilator. W annihilator is a subset of V dash, and we have a basis for V dash, right? Here. So what
So
I can
W
say
is
from
linear
here,
combination of W12 dot WD.
so we have to show that this F belongs to the span of this. How to do that? So this F is in W nor. W nor is a subset of V dash, and we have a basis for V dash, right? This one here. So you just write F in terms of this. So what we know from here that F is equal to alpha I Fi I equal to 1 to n. This much I know, right? Right. But what I
Yes.
can say from here,
Fi
what
equal to I2.
what yeah, so can you say that this alpha is, if you recall whatever we did in the first lecture while introducing this dual basis, since f1 to fn, this is the dual basis of B. If you recall from here, then actually you can say that these alpha i's are actually this one. So you can actually write f as equal to 1 to n. Alpha is actually fwi fi. If you recall from that result, you just look at your notes, and then you will see that while introducing the first definition of dual basis, as a consequence you get this. And why this is true, it is very easy to follow. You know that we can any vector v in V. So let me just recall that here. If you take any vector in V, then you can write it as alpha I Vi. But since you know that these alpha i's are the coordinates, and f1 to fn they are the coordinate function, so you can actually write this as fi of V Vi I equal to 1 to n, right? But then this is true for any vector V. Now if I take this f, any linear functional on V, f in V dash, then what would be f of V? F of V would be, I can write it as fiv fvi I equal to 1 to n, right? But then the same thing is actually, we can say fvi f of I equal to 1 to n, and I can take, because of linearity, this I can write it in this way. But this is true for all vectors V. So this implies that f is actually fvi fi I equal to 1 to n. The same thing I'm writing here. Instead of vi, I'm using the notation wi. Is it okay now?
Yes, sir.
Yes, sir.
Yes. Now from here, what can you say? What can I say from here now? From this step?
F belongs to span of
F belong to span of I equal to,
M plus D plus
yeah,
1.
d plus 1 to n
D plus
fwi.
1 to n.
Yeah, why? Because f belong to the annihilator. So f, the value of f is 0 at w1 to wd. Using this fact, this you can say. So this implies that f belong to the span of fd plus 1 to fn. But f is any element, so this implies that w nor is contained in span of this. So this implies that w nor is equal to span of fd plus 1 to fn, and we are done. So that means dimension of W node is equal to n minus d, and that is what we were trying to show here. So we can say that if V is a finite dimension vector space and W is a subspace of it, then the dimension of V is equal to dimension of W plus dimension of W node. Okay. So let me, before I prove a few more consequences of this thing, let me first give you some examples of how to find annihilator of a set. So let us understand this by an example. Suppose that we are given, let's say, these linear functionals on R4. Okay, and how they are defined: x1, x2. If I take any element here, I send this to x1, let's say, plus 2x2 plus 2x3 plus x4. F2 is x1, x2, again it is defined this way, 2x2 plus x4, and similarly let's say F3, x1, x2, x3, x4 is equal to minus of 2x1 minus 4x3 plus 3x4. Okay, now the question is, you are given these linear functionals on, so these fi's are linear functional on R4 for I equal to 1, 2, 3. So the question is, find the subspace of R4 which is annihilated or subset. So find the subset of R4 which is annihilated by F1, F2 and F3. Okay, so how to do that? We have to find vectors. So what we have to do, we have to find, so let us understand what we have to do first. We have to find a subset S of R4 such that this S is annihilated, by these two F1, F2, F3. What does it mean? It means that if I take any vector V in S, then this implies that Fi of V is 0 for all I equal to 1, 2 and 3. Correct? So this is what I want to do. So first understand that I want to find a set S which is annihilated by F1, F2, F3. Annihilated by F1, F2, F3 means if I take any vector V in S, then it implies that Fi of V is 0 for all these functionals. Right? So any vector V in S would be of the form, S is a subset of R4. So it will be of the form x1, x2, x3, x4. Right? And Fi of V is 0. If I look at Fi here, any of these Fi, they are of this form. And if I put this Fi of this is 0, that means I get a homogeneous system of equation. Right? So this implies here Fiv equal to 0. This implies a system of equations. So S is nothing but, what is S now? S is nothing but the solution space of this system. Right? So S is nothing but the solution space of this system. So I have given you a way to find this S. This is the hint. And now you can complete this. You can solve this system and then you can find this S. So can you do that?
Yes, sir.
Yes.
Yes.
Yes, it is very straightforward now. So you understand how. So this, when I wrote this expression, you might not have consider it in this way. But now if you think again and you write what you want a set S such that it is annihilated by these functional. What does that mean? It means that if I take any vector v, then this is implies that fiv is 0. But if I look at fi, then these are these linear equations. So fiv is 0 means I will get a homogeneous system of equation in, right? Now for this I can solve this system for x1, x2, x3, x4. Whatever solution I get, that would be my uh, this set S. Okay, so you can verify your answer. So I'm giving you the answer here. You finish this and you compare your answer with this. So S would be the set x1, x2, x3, x4 subset of R4 such that x1 is equal to minus 2x3, x2 equal to 0 and x4 equal to 0. This is your set.
Yes, sir. Sam.
Yes, sir.
Okay, good. So now you know that if you are given linear functionals, then you can find the set which is annihilated by the given functional. This you know from this example. At least you have some idea how to do. Now I'll ask the other side question. That means if I am given the set, then can I find its annihilator? Okay. So next, let me do this example here. So what I'm saying is the following. Now let us consider this example. Example 2. So this is example 1. So example 2, what it says that suppose we have a subspace W. So let W be a subspace. This is a subspace which is spanned by these vectors W1. Say W1 is given by this 2, minus 2, 3, 4, minus 1. W2 is given as minus 1, 1, 2, 5, 2, and W3 is given as 0, 0, minus 1, minus 2, 3, and W4 is given as 1, minus 1, 2, 3, 0. Okay, then so we are given a subspace W which is spanned by these vectors W1, W2, W3, and W4. Now the question is find W norm. Not only that, because we know that W norm is a subspace, so find a basis also, and a basis of W norm. Find W norm and find a basis of W norm also. Okay, so let us solve this. Okay. Now here how to do this? So we need to find W norm. W norm means, so again we follow the same kind of idea which we were having in the first example. So we need to find W norm, right? So we have to find. So how did I write? So I'll follow the same language. So we have to find W norm. Okay. What does it mean? It means that if I take any f in W norm, then this implies that f of wi is 0. F of w is 0 for all element in W, but it is sufficient to say that f of wi is 0 for all I equal to 1, 2, 3, 4, because W is spanned by this. So if this is 0, then it is 0 for every W. Do you agree with me?
Yes, sir.
Right? Now this is fine, but here in the previous example these fi's were given. So we could say that okay, this fiv 0 means we have a system of equation. Now do we have something like this here also? Now what is this f? What is this W naught? W naught is basically a subset of dual of R5. So we are looking at these. So let's say this is a subset of R5. Okay, so these W1, W2, W3, W4, these vectors belong to R5 R5, and therefore W any letter is in R5 dash, dual of R5. Now, can you recall something? We have proved a result. We have proved a result that every linear functional. Can you recall something? Every linear functional on a vector
Is a
space.
coefficient of
Yeah.
Is
So can you
coordinate of
recall something? Yeah. No, no, no. So if let me write this. So what we did that if suppose V is a vector space and dimension of V is 5, then every linear functional, if f is in V dash, then this implies that there exists some no, let's say a1, a2, a3, a4, a5 in f5, such that, or let's say it's dimension n, then it's fn, such that f of v is equal to summation ai vi I equal to 1 to n, where these vi's are the basis. So you have to fix a basis also for this. Can you recall this one? We did something like that,
Yes,
right?
sir.
Yes, sir.
So this was
yes,
if
sir.
and only if, right? So here I will use this fact for R5. So I know, so I'll recall now the same thing. So the same thing I will write for R5. So let me write this here. Recall that if f is in R5 dash, then this implies that there exist, let's say A1, A2, A3, A4, A5 in R5, such that this f would be of this form: x1, x2, x3, x4, x5. If I take, then this would be of the form a1 x1 plus a2 x2 plus a3 x3 plus a4 x4 plus a5 x5. So basically I have taken the standard basis here. Okay. So every linear functional on R5 would be of this form for some a1, a2, a3, a4, a5 in R5. Now using this, now you can say you can find a solution. So now come back to this uh, again. So using this fact, what we can say that this implies if f is in W nor, f is in W nor, then this implies that f wi is 0, as I have already written, I equal to 1, 2, 3, 4. But then this implies what? This implies that f wi is 0 means what? If f is in W nor, that means it would be of this form. So this implies that a1, so whatever this wi, so
X1,
basically you write
A1,
this right. So you, instead of this x1, x2, x3, x4, x5, you write this w1, w2, w3, w4, and this will give you a system of equation. So don't worry, I'll solve this. I'm just giving you the idea before we proceed. So this implies that we have so this gives a system of, or homogeneous system of equation, and then we solve this system of equation. So solve this system of equation to find so not every, so any linear functional would be of this form, but not every functional is belong to W nor. There would be some functional which belong to W nor, because W nor is a subset of this. So that means we need to find condition on this a nor, a2, a1, a2, a3, a4, a5. These condition will ensure that this f belong to W nor, and these conditions we get by solving this system. So solve this system of equation to find conditions, to find conditions on these scalars, these coefficient a1, a2, a3, a4, and a5, so that this f belong to W nor. All right, so this is the idea. Now I think things are clear. Now if you put this f, let us suppose that f belong to W node, any f is of this form here, then this would, if f belong to this, then fwi is 0. You just put this fwi 0 for each I equal to 1 2 3 4. So that means you replace this x1 x2 x3 x4 x5 by this. So this will give you 4 equations, right? So this implies that we'll have system of equation. I'm directly writing this system of equation here. What it would be? The first would be, if you look at here, 2 minus 2 3 4 1. So it would be 2 minus 2 3 4 minus 1. Then it would be multiplied by a1 a2 a3 a4 a5. So I'm writing it in this way, right? And then the second would be minus 1 1 2 5 2. This is W2, coefficient of W2, and then W3 0 0 minus 1 2 3 minus 2 3, right? And then 1 minus 1 2 3 0, and this is equal to this one, right? Now if you solve this system of equation, then you know, when you find the system, this solution, you will get condition on a1 a2 a3 a4. So for example, when you use this Roy-Klein form, then the Roy-Klein form of this would be, of this matrix would be, I'm directly writing this, 2 minus 2 3 4 minus 1 0 0 7 14 3 0 0. You can verify this, okay? I'm saving some calculation time here, and the last row would be 0. Okay, so this is actually row equivalent form of A. So if I call A to this matrix, okay. But what does it mean? So what condition it gives you? It gives you, when you now solve this system, this which is the reduced form, and you will get condition on this coefficient. The A1 would be A2 plus A4, A3 should be minus 2A4, and A5 should be 0. This is the condition you get. Therefore, now you can write that if f is in W node, then f would be of this form, where these scalars a1 a2 a3 a4 5, they should satisfy this condition. So what you can write is that this is true for any element of W node. So you can say that W node is actually collection of all linear functional on R5 such that f x1 x2 x3 x4 x5 is equal to, of the form here, of this form, every function would be of this form, but now we have condition on a1 a2 a3 a4 a5. So I'll write this condition. So a1 is basically a2 plus a4 x1 plus a2 x2, a3 is minus 2a4, so 2a4 x3 plus x4 a4 x4, x5 is 0, a5 is 0, so we don't have to write this, and these a2 and a4, these are free, they belong to R. These are scalars coming from R. So now this is a set, this is in fact a subspace, this is a subspace of R5 which is annihilated, which annihilates W. This is a subspace of R5 dash which annihilates W. Now can you tell me what would be the dimension of this W node?
2, sir.
So clearly, because there are two free A2 and A4, there are two free variables here to define these functional. So dimension of W node is clearly 2. Now from here also you see, but you can also say dimension of W node. Just to cross verify this, you can check that this is also true, because dimension of W is 3. So dimension of W is 3, then using the previous result, we can say that dimension of W node is Now we have to find a basis also for this. So how to find a basis now from this W naught? So there are two free things, A2 and A4. What I will do, I will first put A2 equal to 1 and then A4 is 0. If I do this, then I'll get a functional A1, a particular function here in W naught. What would be this? F1, let's say call this F1. It is equal to, so A2 is 1, so it is just x1 plus x2. Then A4 is 0, so it is just x1 plus x2. And when you set A2 is 0 and A4 is 1, then you get F2, x1, x2, x3, x4, x5. This is equal to x1 minus 2x3 and plus x4, right? Now you can verify that this f1 and f2, they form a basis of W naught. Okay, you can simply verify. This is very easy to verify because the way we have chosen this f1 and f2 by setting a2 1 and a4 0 for the first functional, and the second function for the second functional a2 is 0 and a4 is 1. So this you can verify to convince yourself. All right. So this is how we can find any letter of a subspace. Now, is it okay? Any doubt, any problem in whatever we have covered in today's lecture? So I won't start anything new because there is only, I think, 4 minutes. So if you have any doubt, you can ask. Whatever the syllabus of minor exam would be, whatever we have covered so far. So whatever is covered till today's lecture would be there in the minor exam. All right. So we can stop here, and then I'll see you at 4 o'clock. I'll share a link to join the meeting. We'll do it in the same way. The main purpose of that session is to see how you have thought about those problems and how you have written also. Okay. Again, as I mentioned earlier, in the exam, the questions won't be difficult, but you will have to think a bit. You have to use whatever you have studied. If you just use just know the definitions and the basic results, you will be able to do the questions. So just think of the problems I have shared. Try to think independently. Doesn't matter if you make mistakes. Just share your doubts or share your like difficulty in solving those problems in today's session, and then we will try to see how I can help you. All right, we can stop here now.
Thank you, sir.
Yeah.
Thank you, sir.